Hi, everyone. Thanks for coming to watch my talk. Today, I'll be discussing the implications of various modeling systems and the insights that they provide us for protecting a great group of fishes. There we are. You might be wondering, what is a skate? So they're actually the most diverse order of cartilaginous fishes with over 285 species. All of these species lay eggs, but the even more interesting fact is that the morphology of each of these egg cases is specific to that species. So the eggs are deposited onto the sea floor from the mother, where they will then remain throughout the embryonic development, which can be anywhere from a period of 1 to 3 years, depending on the species and also the temperature in their surrounding environment. So the species of the North Pacific Ocean structure nursery sites, and these are locations where adult females repeatedly frequent the same area and lay thousands of eggs over the course of time. So we know currently of 25 specific nursery sites throughout the Alaskan seas. And while we regularly catch adults and egg cases of 2 specific species in the Salish Sea, we have yet to find any large nursery structures here. So one of the biggest differences between these two tidal models that I'd like you to look at are the drastic differences in velocity between the nursery sites that are found in the Alaska Sea and Eastern Bering Sea, which are about at 20 centimeters per second of current flow, compared to those that are highlighted or circled in the Salish Sea, which can vary anywhere up to 75 centimeters per second or more on an average day. So we aim to identify if the Salish Sea is in fact a suitable region for nursery sites by modeling the egg cases themselves and their individual hydrodynamics. While egg cases exhibit similar macrostructures, being the basic anatomy, those are the capsule, the horns, and the lateral keels. The size of the case and the morphology of these structures are highly variable. So the first 4, we have the baby Raja species, and these are all species from the Eastern Bering Sea. And our last 2 species, Binoculata and Rhina, are local to the Puget Sound. So these are going to be our comparison groups. And we're specifically interested in the role that macrostructures play in aiding these egg cases to achieve such long residency, and further how the shape of each egg case affects the drag that it experiences in changing currents. To better understand the hydrodynamic capabilities of each egg case, we tested every individual 3 times and in each of these orientations to flow in the flume. So anterior to posterior, posterior to anterior, and lateral. To simulate a consistent environmental substrate, we used a medium level coarse sandpaper. And also to simulate different currents, we increased the velocity by 1 inch per second for every 10 seconds. And then we eventually recorded the max speed at which the egg case broke contact with the substrate. And this is what we call our breakaway speed. So here we're looking at the species that showed a significant difference in their orientations with relation to flow. And we can see that different species exhibit varying orientation biases to flow with regards to speed. And here in the anterior region or bias, we have Interrupta and Permifera, which exhibit the anterior horn orientation bias. And the least likely, but most likely for Trichera, is the lateral orientation to flow. And so this is actually the only species that we found that had this favor towards being in a lateral position, which for the other ones generally resulted in them kind of tumbleweeding off of the substrate. So in the last category, we have elutica and binoculata and rhina, and these all exhibit a posterior horn bias to flow. When comparing fluid regimes, we generally think about the flow around an object belonging to one of the two major groups. So either being to a laminar type of flow or turbulent flow. But in nature, flow around an organism is rarely always laminar, and it generally ends up becoming more turbulent in a changing environment. So in order to entangle the variables of size and shape across egg cases and to visualize the various fluid regimes, we created an idealized flow system using CFD models. And I'll let this play on a loop and I'll kind of talk through it all. But here we have scaled all of the egg cases to the same median lengths in order to focus on which shapes create the most drag. In other words, which species have a lower threshold for fast currents. So we can see that the fluid regimes visualized around interrupta at the top and binoculata at the bottom at 20 centimeters per second, which is our idealized or simulation of currents based on the Alaskan nursery sites that are known. So the color system here, the color scheme, the teal to pink transitions indicates increasing velocity, and the yellow lines show the velocity streamlines. And lastly, the blue lines indicate the changing vorticity. So this is kind of the most interesting factor that I'll focus on for now. So we can see that the flow behind interrupta remains separated for a longer period of time and flows back to a farther distance until it stabilizes. And this indicates that it has a larger wake compared to that of binoculata, which ends closer to the posterior horns and stabilizes a little bit faster. So overall, the horns provide a stabilizing effect where there's a minimal jump in vorticity at the anterior and posterior of the egg case. And this is due to the presence of the horns, which also lowers the chances of that rolling effect that I was talking about. Next, we have the lateral view of the egg cases in our idealized flume. Similar to the horns that provided a stabilizing effect, the lateral keels in this lateral view provide a stabilizing effect to aid in the continuous flow around the egg case, which we see in interrupta. But the big difference that we see for binoculata is the orientation. Their modified dorsal keels are actually kind of inhibiting them or causing more of a disruption than they would in the anterior posterior position. So what would be advantageous in an anterior posterior flow, these keels on the top of the capsule, hindering them in a lateral view where the dorsal keels are breaking up the flow and causing more changes in vorticity. So this also creates more drag and, like I was saying, increases the chances of this egg capsule rolling, or in this case, potentially being reoriented to have the horns face flow in an anterior or posterior position. So here we have the theoretical drag based on the morphology of each egg case at a constant velocity of 20 centimeters per second. And we calculated the drag coefficient based on an equation for the wetted area of a streamlined object. And what we can see here is that our bigger shapes in general have higher drag than the more streamlined species like Rhina, which has a lower drag. So in order to compare our models of theoretical drag and the CFD computed drag, we gathered the pressure differences across the anterior, top, and posterior of the egg case seen in P1, P2, and P3. So we did this in order to calculate the pressure differential across its cross-sectional area, which gives us the drag force of our scaled egg cases. So we found the same trends in pressure drag as we did when computing our theoretical drag. You can see here that the bigger shaped species, even when scaled to the median value, still exhibit a higher drag. And this is more so based on shape than, again, size. And this is indicating that the morphological variables are strong predictors of not only the drag each species experiences, but also the optimal flow that they might be found in. So a lower drag, again, means that the species can withstand higher rates of flow and therefore are less prone to rolling away from the nursery site. So we might expect to see Interrupta and Rhina in more of a flexible environment that has higher changes in flow, Inoculata and Permifera that have a lower tolerance to high speeds. So our major takeaway is that the morphology-driven modeling can be a great indicator of the hydrodynamics for skate egg cases. And using species with known habitat sites allows us to interpret where the others, where we don't know where they are more likely to be. And from our modeling, we can tell that the Salish sea species Inoculata cannot handle as high of currents compared to Rhina, which indicates that we're more likely to find them in regions where the islands have a much slower flow. And now we just need to go search for these nursery sites and find some more egg cases. So with that, I'd like to thank everyone who supported me and this work. And I look forward to answering any and all of your questions on the SICB+ forum. Thank you.